Okay, thank you, Father Thomas, very much. It's a real pleasure to be here and to be part of this conference and to visit Rome, as always. My wife, Cynthia, and I have been enjoying ourselves the last few days in the Eternal City. So what I'm going to talk about and what I think I was assigned to do by the organizers was to give you the best scientific assessment of what the future evolution of the solar system is going to look like. And then my friend and colleague, Father Jonti, will talk about the entire universe. Much of what I'm going to talk about is not so much speculative as it is, I would say, both statistical for some of what I will talk about, and also somewhat of an extrapolation of what we understand of the way that stars behave, stars that we can see in our galactic neighborhood, that we can observe and measure, and that gives us a sense of the evolution that is likely to happen for our own sun. Now, no one can predict the future, and of course the whole basis of the scientific method is that what we see empirically or what we observe in nature allows us to make these extrapolations, but they are really extrapolations, so bear that in mind, please. So when I talk about the solar system, I want to give you first a very brief overview of what the solar system is. The solar system, by definition, is everything that is gravitationally bound to our star, the sun. And that includes not only the 8 planets plus Pluto. I happen to call Pluto a planet, but it's generally thought of as a member of the Kuiper belt of so-called dwarf planets beyond Neptune. But in addition to the planets themselves, there is a vast cloud of debris that has been ejected from the inner part of the solar system and lies at a great distance away. This is called the Oort cloud, extending out perhaps a third of the distance to the next star, Proxima Centauri. But I want to focus on the planets because they have the most mass in the system. And so you're seeing 2 diagrams here. And let me see if I can bring the pointer up. There it is. Okay. So in terms of size and mass, the giant planets are really most of the mass of the solar system. In fact, Jupiter itself, which is 300 times the mass of the Earth, is most of the mass of the solar system. Saturn is second. So the sizes, the relative sizes, are shown in true scale on the upper figure relative to the disk of the sun. And the inner part of the solar system consists of small planets that are rocky, Mercury, Venus, Earth, and Mars. And then beyond the asteroid belt, which contains almost no mass at all, and may have had a larger amount of material in it that was ejected by the gravity of Jupiter. Beyond that are the giant planets. And if you look at a properly scaled version of the solar system, which is the bottom figure here, you see that the inner planets are clustered quite close to the sun, and the giant planets are spread out over a much larger distance. If they were scrunched in closer together, we would not see the giant planets because they would have interacted gravitationally and ejected each other from the solar system. So actually, even though the giant planet system looks spread out, this is about the most compact system you can have with the masses of the giant planets that we actually observe. So there's one unit that I want to introduce you to, which I'm going to use later on, and that's the astronomical unit. The astronomical unit is the distance from the Earth to the sun. It's 93 million miles, or 149 million kilometers. The actual distance was measured in the late 1700s by observing the transit of Venus across the surface of the sun. So that's the field that we're going to be talking about. That's our cosmic home. That's where the Earth is as one of the planets of the solar system. I also want to give you a sense of what we're going to be talking about in terms of time. And we're going to be talking about billions of years, which is, for those from the UK, 1,000 million. And the reason that we're going to be talking about those timescales is that that seems to be the general timescale of things not only in the universe, but in our solar system as well. And to determine those timescales, there have really been three nearly independent approaches, one of which is the dating using unstable isotopes of certain elements of rocks on the Earth, on the Moon, and in meteorites, which are leftover debris from the formation of the solar system. Those give ages for the solid material in the solar system of 4.566 billion years. And is quite an accurate approach that is in many ways self-correcting. The second approach is to look in detail at the properties of our sun and to match that with models of the evolution of stars as they convert hydrogen into helium, and that is the source of the light of normal stars like the sun. That is something that is calibrated and tested by looking at many, many stars elsewhere in our galaxy, particularly stars that are in clusters, where the clusters represent stars that formed at the same time, but stars of different masses and brightness will evolve in different ways. And the final approach is the very famous Hubble's law, which has now been properly, or at least recommended to be properly renamed the Hubble-Lemaitre law. It's the relationship between the velocity at which galaxies seem to be moving away from us, actually trapped in the expansion of space itself, and the distance to those galaxies. And it was first actually derived theoretically by Georges Lemaitre, who's a Catholic priest, Monsignor, and also a very famous and gifted cosmologist, and then empirically determined a few years later by Edwin Hubble. All those techniques tell you the same story, that we live in a solar system and a cosmos that is billions of years old. It's very difficult to get around that. It's also a timescale that's hard to wrap your brain around. We are beings that live for 70, maybe 80 years if we're strong, as the Psalm says. So to give you a sense of what that means in terms of events up till now in our universe and solar system, I'm going to essentially take that 13.7 billion years, which is the age of the universe, and compress it into a calendar of 12 months, the cosmic calendar. It was really, I think, Carl Sagan who first did this. It may have even preceded him. So here you see this calendar. January 1st, right at New Year's, is when the Big Bang occurred. And much of what happens in the first 8 months is going to be the subject of Father Jonti's talk, so I'm not going to discuss that. Our considerations begin on September the 3rd in the cosmic calendar, which is the equivalent of 4.56 billion years ago, or about 9 billion years into the universe itself. It's also my sister's birthday, so it's very convenient locus there. And that's when the Earth and the solar system formed. And then the geologic record says that life began, the first primitive cells, very soon after that, maybe 2 weeks in the cosmic calendar after the Earth forms, where the whole history of the Earth is the remaining 4 months. So life begins very quickly, but remarkably, it takes a very long time for complex cells of which we are comprised, to arise on the Earth. In fact, it takes a period of 1, 2, 3 months until we get to sort of early to mid-December. And on December the 17th on the cosmic calendar, the first complex animals, the first multicellular differentiated animal forms appear quite suddenly in the Cambrian explosion. And then human beings appear at 5 minutes to midnight on New Year's Eve. So we are a very late development in the history of the Earth, and therefore our perspective is one of a species that has come along very, very late in the history of the Earth, but has to think about billions of years. And it is the remarkable thing about the human mind that we can do that. Lemaitre himself had some interesting things to say about that from a philosophical point of view, which I will, if you want to know about it, ask me about it. So what makes this solar system that I'm going to talk about a livable place? And the answer is relative stability. And you can see that just by looking out at the Earth. This is, I've stolen this image from a book that was one of my treasured books as a child. Look Out the Window was published in 1959. So if you look out the window, you find that the orbits of the planets are very stable. They're stable over billions of years. That's not necessarily the case in other systems. The sun's brightness is very, very stable. It hardly changes at all. The tilt of the Earth's axis, which determines the amplitude of the seasons, is nearly constant thanks to the presence of a large moon that kind of screens out the effects of Jupiter, which otherwise, as we've learned from Mars, might cause our planet's axial tilt to wobble back and forth by quite a large amount, which would change very dramatically the intensity of the seasons. Most of the big leftover debris in the solar system from the formation of the planets has been cleaned up. There are impacts that occur, but they're generally impacts of small bodies. Early in the history of the solar system, the Earth itself might have been struck by a body the mass of Mars. That might have been the origin of the moon. There are various arguments for that. But that doesn't happen today, and that's good because that would wipe out all life on Earth instantaneously. And finally, the galactic neighborhood in which the Earth and the solar system are located is relatively sparsely populated. We're out in the suburbs of our Milky Way galaxy. We're not close to the center. The stars that are around us tend to be relatively low-mass stars, and so any stars that are massive enough to become supernovas, to explode, are quite a distance away from us, and that's advantageous. So it seems like we're in a very friendly part of the universe and time in the history of the solar system. But if you look out the window a little bit more closely, the view isn't quite as friendly as in that childhood book. That stability that I talked about, that planetary stability, is actually marginal. Jupiter and Saturn are in a relationship that's called the Great Inequality, which I'll return to at the end of this talk. And it has to do with the fact that they're very, very nearly in what's called an orbital resonance. When Jupiter makes 5 revolutions around the sun, Saturn makes approximately 2, but not quite. So resonance is a situation where the ratio of the orbital periods are small integers, 1 to 2, or 2 to 3, or 2 to 5, that sort of thing. Resonances tend to make planetary orbits unstable. It's easy to perturb them and cause those orbits to go from nice, relatively circular orbits to very stretched out ellipses, where a planet like Jupiter would end up moving through the entire solar system, kind of like a giant bowling ball, and knocking everything out of their orbits, like the Earth. So the fact that these two bodies are close to a resonance like that is a very interesting situation, and that will play a part in the ultimate end of the solar system, as I'll talk about in a few minutes. The sun is stable, but it has a finite amount of hydrogen that it can convert to helium. It can't convert all of the hydrogen. It's only the hydrogen in the very innermost part where temperatures are high enough for fusion to occur. The moon is actually moving away from the Earth, not because it doesn't like us, but because the spin of the Earth, the 24-hour spin, is much faster. The period is much shorter than the period of the moon's orbit around the Earth, and that period is exactly I do this to my classes, and they get totally annoyed. The time it takes for the moon to orbit around the Earth is 1 month, okay? Month, moon. So because of that, the Earth and the moon are interacting gravitationally. There are bulges that are raised on the Earth, particularly in the oceans of the Earth. Those bulges create torques on the moon, And so they're coupled together, but because the Earth's spin is much faster, the net effect of that torque is to give the moon some of the angular momentum of the Earth's spin. And so the Earth's spin slows down, the day is getting longer. We see that in the geologic record. And the moon is getting more angular momentum, which means that its orbit is spiraling outward. Now, as it spirals outward, as we'll see, its influence in keeping the axis of the Earth relatively stable in terms of the angle at which it's pointed, that influence will go away. There are rare events that can cause large asteroids to cross the orbit of the Earth and hit the Earth. And then finally, supernovae do happen, and the Earth is not fixed in its place in the galaxy. It is orbiting like the rest of the stars around the center, but it's also moving relative to that orbit. The whole solar system is moving through the galaxy, and we might blunder into a region where there is a supernova someday. So what are the threats to humanity? I know I'm supposed to talk about the end of the solar system, but inevitably, we're really interested in what that means for the end of humanity from a physical point of view. So here's a list, and interestingly, you can order these sort of by factors of 10, which is what I've done. I haven't mentioned the species lifetime limit for mammals, but that's the first thing I'm going to get to. That's 1 to 10 million years. Extinction level impacts where, for example, the dinosaurs are wiped out. Those seem to occur about once every 100 million years. And extinction level supernovas where we are in the galaxy maybe once every billion years. Now, these are statistical threats. These are things where you don't know whether an event like this is going to happen tomorrow or in a million years or will never happen, because they depend upon things that are contingent or stochastic on events that are very difficult to predict. The items after this in the boldface are things that will happen if our understanding of the way that the physics of planetary orbits and stellar fusion occur, if those are well understood. So these are not statistical now. One is the loss of the axial stability of the Earth's tilt. That's on the scale of 1 billion years as the moon moves farther away. The rising brightness of the sun. The sun is not stable on very long time scales. I'll explain why that is. That also, in somewhere between 1 and 3 billion years, will cause our climate to be much warmer than it is today, to the point that the oceans may evaporate away. And then really exciting things happen, Hollywood-style things happen on a scale of 10 billion years, which is the sun will eventually use up its usable hydrogen in its core, and it will expand to become a red giant and probably will engulf the Earth. And I'll talk about that. Oh, that's caused a lot of rustling. Okay. That is a long time from now, so don't leave the room in a panic. Everything is stable. And then the ultimate end of the solar system, which hardly anyone talks about, is that the giant planets are going to eject each other. That's the end result of the great inequality, and I'll explain that at the end. All right, so very quickly, mammalian species in the fossil record seem to last between 1 and 10 million years. This may be a combination of genomic exhaustion and natural selection. Modern humans arose maybe 100,000 years ago, maybe 200,000, so we're relatively youthful species. But the point about mentioning this is that if we as humans are subject to the same natural selection that Darwinian evolution shows other species are, we won't be around to see these other exciting events. If humans become extinct, become transformed into a different species, in 1 million years or even 10 million years, all of these other catastrophes are really irrelevant. And there are lots of fun science fiction stories. Arthur Clarke has a theme in his novels where there's a sort of divine intervention that pushes humans into the next phase of evolution. Greg Bear had a series of 2 or 3 books in which our own genome, as humanity becomes too abundant on the Earth, our own genome sort of triggers an event where a piece of DNA that was inherited from viruses. And by the way, somewhere between 1 and 10% of our genome is probably viral, suddenly triggers a change of species. As a 63-year-old professor, I'm ashamed to say that my interaction with students these days is suggesting that that change has already occurred, but that's probably in me and not in them. So I won't say any more about this because we don't know when or if that'll happen. I mean, technology is such that we could avoid natural selection. And maybe the human species will live 1 billion years, who knows. Impacts are interesting because there's evidence in the geologic record for great extinctions. This is a summary of that. This is the number of families in the sense of the phylogenetic tree, the Linnaean scheme of classifying organisms, versus geologic time since around the Cambrian explosion, when the first animals could be seen in the fossil record, because before that, it's really just microbes and plants, and you can't really get a sense of loss of diversity in things that are just kind of single-celled organisms. And what you see is a rapid rise in the number of families, and then there are these little teeth or cutouts in this rise, the biggest one being at the end of the Permian era. And these are great extinctions. These are times when large numbers of families, which translate into species, simply disappear. Now, the best documented one is the most recent one, 65 million years ago, the Cretaceous Tertiary extinction, where there's geologic and chemical evidence that the event that wiped out the dinosaurs and many other types of organisms was caused by an impact, about a 10 or 20 kilometer size asteroid that impacted in the Gulf of Mexico off the Yucatan coast and actually left an impact crater that has been buried by sediment, but was revealed by oil exploration by the Mexican petroleum company Pemex in the 1970s and 80s. And so there's a crater under there in the Yucatan. It dates to that time. There's lots of evidence and sediments around the world, including here in Gubbio, of this layer of iridium that would have been deposited by this impactor. Now, whether these other extinctions are caused by other impacts of large bodies on the Earth or not is not at all clear, but based upon what's seen in the solar system, it's reasonable to think that one dinosaur-killing impact occurs every 200 to 250 million years. That's a recent estimate. Smaller impactors are more frequent. Larger impacts are less frequent. If we had a dinosaur-killing impact, humans would probably survive, but our civilization would not. There'd be massive starvation, food chain disruption, darkness for periods of weeks or months, so on and so forth. But something like that probably would not wipe us out. If there were something 100 or several hundred kilometers in size, that would probably wipe out all life on Earth, but that's based upon the statistics unlikely to happen on a timescale of perhaps billions of years. Now, supernovae, the last of the statistical ones. Here's the Crab Nebula. It's 7,000 light years away. It's about 12 light years across. Something like that, when a star explodes, what has happened is that it has undergone fusion of all the elements that can actually donate energy as a result of fusion. And so there's simply no source of energy left. The star collapses. A star the mass of the sun will not blow up, but it will lose mass as during the collapse it kind of expands again and begins another phase of hydrogen fusion. Massive stars do that sort of oscillation, but when they finally have finished doing any fusion at all, in this case the production of iron, they simply collapse. And the tremendous energy that is caused by that collapse then creates a disruption, an explosion, in which most of the star simply gets dispersed into space. And that releases a large amount of what's called gamma radiation, which for a nearby planet could strip away the atmosphere or so damage the DNA of any organisms that they would no longer be able to reproduce. But within 10 parsecs, that happens every few hundred million years. That could be survived. It would change temporarily the climate of the Earth. It would strip the ozone layer away. And there aren't any real nearby candidates at the moment. But the thing to think about is if you map the trajectory of the sun through the galaxy, which is actually influenced by the spiral arms of our galaxy, the sun has actually moved a large distance inward and outward in the galaxy. And this is a simulation of that by Alice de Biasi, who was a student at Padua who finished her Ph.D. at Cornell some years ago. And what's shown here on these graphs, the upper left one, is the distance in thousands of parsecs. A parsec is about 3¼ light years. That's a distance measurement that astronomers use because it's related to the phenomenon of parallax, which is a way to measure distance to the stars. So our galaxy on this scale is about 30,000 parsecs. And without the spiral arms, you see the green line, the sun and the solar system, stay within 1,000 parsecs of their current position. It's very regular. But the spiral arms of the galaxy perturb the motion of the sun so that it may move over its history many thousands of parsecs, perhaps into regions where there are large numbers of supernovae. And then there's an up and down motion, which is shown on the lower right, which is only about 100 parsecs and probably doesn't change very much the environment that we're in. But it's possible that the sun will blunder at some point into a region where a supernova is more likely. So now I want to talk about not the statistical potential ends of humanity, but the ones that are simple extrapolations. So the loss of stability of the Earth's rotation axis. So very quickly, the moon stabilizes the axis of the Earth against the effects of Jupiter. As the moon moves outward with time, it has a weaker and weaker gravitational effect on the Earth's spin. Eventually, Jupiter's effect will take over because Jupiter's very massive, even though it's distant, and it will pull the Earth's rotation axis in a kind of a stochastic way. That happens to Mars. Mars does not have a big moon, and there is a set of very well-defined mathematical models that predict that Mars's axial tilt, which today is similar to that of the Earth, 26 degrees instead of 23 degrees, might go all the way from 50 or 55 degrees up to 10 or 15 degrees, which would be a huge change in the climate over long periods of time for the Earth. But again, humanity, if it's still around, a few hundred million years or a billion years from now, would probably survive that. What we may not survive is the end of, or the evolution of the brightness of the sun. And this is on a billion-year timescale. So our planet is habitable because liquid water is stable on the surface. And liquid water is stable because the energy we get from sunlight, which is absorbed by the Earth's surface and by the lower atmosphere and plants, gets re-radiated as infrared radiation, and that warms the surface of the Earth. Energy in is energy out, or more precisely, the average power, the average energy per time coming in is equal to that going out. Now, it isn't just the direct sunlight, because in fact, the Earth's atmosphere contains gases which absorb infrared radiation, that's light at longer wavelength than visible light, and water and carbon dioxide do that. They absorb that energy, which makes it harder for that energy to get out, so the energy coming in comes in very easily through our transparent atmosphere. The energy going out goes out more slowly, and so the more of these gases are present in the atmosphere, the more the temperature gradient, the temperature as a function of altitude, has to steepen in order to allow that flow of energy out. And that's the essence of the greenhouse effect. Now, we tend to think of carbon dioxide as the greenhouse gas, but water is a powerful greenhouse gas. It's controlled not by human emissions or plants or anything like that. It's controlled by the evaporation of ocean water. The surface temperature of the Earth gives you a certain temperature of the oceans. Now, the sun is stable on short time scales, but on long time scales, it's gradually getting brighter. The fusion reactions that occur inside the sun involve taking 4 protons, those are the nuclei of hydrogen, smashing them together in a multi-step process, and making a helium nucleus of 2 protons and 2 neutrons that are tightly bound together. And they're tightly bound because, in effect, that's the more stable state for those particular atomic particles. As a consequence of that binding, they've effectively lost mass relative to 2 protons and 2 neutrons just flying around freely. And that lost mass, by Einstein's equation, E equals mc squared, goes into energy, and that's the energy of starlight. Now, why do we even think that's happening inside the sun? Well, the intermediate products of those reactions, like an isotope of helium called helium-3 and a heavy isotope of hydrogen, deuterium, are actually seen in the solar wind. The wind that's coming from the sun has that debris. And there are very exotic light particles called neutrinos, which pass through walls very easily, but can be captured if you put a huge vat of literally cleaning fluid, dry cleaning fluid, down under the earth in a gold mine where only these neutrinos can reach. Other particles are screened out. And those neutrinos are seen as well. And of course, nuclear fusion has now been done in the laboratory. So pretty firm. The main point here is that if I take 4 particles and I make 1 particle out of them, I'm decreasing the number of particles in the sun. And because the balance of forces that give us this gaseous sphere of the size that it is, the balance of forces is the outward pressure associated with a very high temperature, the collision of these particles inside the sun. The inward force is the force of gravity pushing in. As the number of particles goes down, that pressure outward would want to decrease if the temperature stays the same. And so the sun will tend to compress as it goes from something that has a certain number of hydrogen atoms to something that has more and more helium atoms, and in net form, fewer and fewer atomic particles. So the sun will shrink, but that shrinking causes the gas to compress, and that compression then causes the gas to heat up. So fusion reduces the number of particles, the sun wants to shrink, that compresses the gas, it heats it up. Fusion is very, very temperature dependent for reasons that I won't go into here that has to do with quantum mechanics. And as a consequence, that compression, as it raises the temperature, causes the fusion reactions to go faster and faster. Faster fusion reactions, brighter sun. So over time, and this can be seen by observing stars of different ages, the brightness of the sun is going to increase. Now, how much will it increase? Well, eventually, before the sun finishes its hydrogen fusion, it'll increase to almost twice the luminosity it has today. 4 billion years ago, it was 70% of the brightness that the sun has today. But long before that, when the sun reaches perhaps 105% or 120%, that is 5% or 20% larger luminosity, something really bad will happen if you like the ocean, which I do. As the light from the sun increases, as the sun gets brighter, the surface temperature of the Earth will have to go up because the average power in is the average power out. And as the temperature of the surface goes up, just due to the brightness of the sun, the rate of evaporation of water from the ocean, which is also very sensitive to temperature, will go up. In fact, it goes up exponentially with temperature. As water is driven from the ocean into the atmosphere and becomes water vapor, it will increase the greenhouse effect because water is a greenhouse gas. And so the temperature will go up even more. Now, there's no safety valve on this because eventually you get to the point where evaporation is strong enough that that water vapor driven into the atmosphere will again heat the surface up enough that more water will get into the atmosphere, which will make it even higher temperature. And even with no carbon dioxide in the atmosphere, the models remember these are computer models, say that so much water will be driven into the atmosphere that it will flow out into the stratosphere of our atmosphere. Now, what is the stratosphere? The stratosphere is the part of the Earth's atmosphere which is at or just above where jetliners fly. And it's a part of the atmosphere where the air is thin enough that as that water vapor drifts further upward, diffuses upward, it will be exposed to ultraviolet radiation from the sun, which is screened out in the lower layers of the atmosphere, mostly screened out by ozone. So what will happen to the water when it's exposed to ultraviolet light? The ultraviolet light has enough energy that it will break the bonds between the hydrogen and the oxygen in water. Remember, water is H2O, 2 hydrogens, 1 oxygen. It will break those bonds. The hydrogen will be liberated. Yippee, I'm liberated, I'm a hydrogen atom. Oh, this is a tough crowd. That hydrogen is really lightweight compared to the other components of our atmosphere, the nitrogen, the oxygen, and so on. So it will just escape. It will flow away from the Earth. And some of that's even happening today. You can see a hydrogen corona around the Earth, but very, very slowly, because in the present time, the temperature at the boundary between the troposphere and the stratosphere is very low. That's a very cold part of the atmosphere, so water is bottled up. But as more water goes into the atmosphere from this brightening sun, that temperature at the boundary will increase quite a lot. Water will flow upward, get broken up into hydrogen and oxygen. The hydrogen will escape, and the oceans will be gone. When will that happen? Sometime between 1 and 3 billion years from now, we'll go from looking like this on the left to this picture of Venus, where this may have happened early in its history, where there's no water on the surface at all. And I have to say that John of Patmos seems to make particular mention in his description of the new heavens and new earth, where he says, and the sea was no more. He just really makes that point right at the beginning. And the sea will be no more. There will be no more ocean. Now, there may be some residual water at the poles of the earth. Whether there will be or not depends on your model. Whether life could survive there is unclear. But that's the end of the oceans. And whether humans, if we survive, this is 3 billion years from now, would actually be able to live on an oceanless Earth is unclear. If that doesn't kill us, the next step will. So 7.7 billion years from now, and that number is pretty precise based on stellar models, the sun will simply run out of fusible hydrogen. The temperatures in the core allow fusion to occur. The core will become entirely helium. Further out, really, I've got 8 minutes on my clock. I have 37 minutes here. All right, and we have 8 billion years left. So at that point, the core of the sun will be helium. Fusion will stop. The sun will lose its thermal pressure support. It will begin to collapse. But instead of going supernova, the models tell us that helium fusion will begin, which requires higher temperatures. Helium making carbon and oxygen. And that will heat up a layer outside the core, which then can start hydrogen fusion again. The net result is the sun begins to expand as this new energy source becomes possible. And it becomes a red giant. And you can find red giants elsewhere in the galaxy. They're very well studied. The sun will swell up to about 250 times its current radius. The distance from the sun to the Earth today is 210 solar radii. So if you've been paying attention, that's kind of bad. The surface of the sun will not simply be our next door neighbor, we'll be living inside the sun. And the luminosity of the sun will be almost 3,000 times the present value, and so the zone of stable liquid water will be out at Pluto, our dwarf planet. However, the sun is blowing mass off like crazy as this is happening in the form of a nova, planetary nebula. And as the sun loses mass, Newton's law tells us that the orbits of the planets will expand. So the Earth will move away. That's good because the sun is coming up. However, this is not quite so simple as it sounds. The sun's rotation rate, as this material is being lost, the sun's rotation rate will slow down because the angular momentum associated with the sun rotating today every 26 days, few weeks, that angular momentum will be carried away by this material. And the reason for it gets into magnetic fields and so on that I don't have time to talk about. And it's possible that this is wrong, but the observations of red giant stars seem to show that they have slower rotation rates than normal stars like the sun. So maybe it is right. So why do we care about that? The sun's rotation rate could slow down to the point where the period of rotation is longer than an Earth year. And if that happens, then the tidal interactions between this ballooning sun and the Earth will be the opposite of what the tidal interactions are today between the Earth and our moon, where the spin rate of the Earth is faster than the orbital motion of the moon. In other words, instead of the Earth pulling away due to tidal effects, the Earth will donate angular momentum to the sun and it will start to drag inward. So losing mass, the Earth's orbit expands. Tidal interactions, the Earth gets dragged in. Which one wins? No one knows. It's very complicated. The latest models suggest that tides win, and so I'm showing you the latest model here from Schroeder and Smith. This is distance in that famous astronomical unit versus time in millions of years, not from today, but from the point where the sun begins its new life as a red giant. So this is a period of millions of years in which the sun, now burning helium, is expanding. You see the radius is going up and up and up to beyond 1 astronomical unit. At the same time it's losing mass. These little points here, 0.9, 0.8, 0.7, that's the mass of this red giant star, 90% the mass of the sun, then 80%, then 70%. And the dashed line is the orbital distance of the Earth from the sun. So as the sun loses mass, the Earth would like to expand, the orbit would like to expand, but the sun is pulling the Earth in by tides, and in this simulation at least, the net result is that the sun wins and the Earth gets engulfed in the atmosphere of the sun. It will simply become a molten blob, but then the drag of the atmosphere of the sun will cause it to simply fall all the way in, and the Earth will be completely done. Now, we can fix this problem by moving the present-day orbit of the Earth out by about 15%. And maybe we can actually do that, or humans a billion years from now, by redirecting some asteroids to make close approaches to the Earth and donating some orbital angular momentum to the Earth. But I'll leave that for the future. All right, so this is a debris, a planetary nebula from a star that did a similar thing, the Cat's Eye Nebula. The planetary nebula is in the center. This is debris that has come off of the star itself. The solar system would be very close to the center here, very hard to see. So the sun itself will become a white dwarf. It will begin to cool down, and whatever is left, which would be Mars, Jupiter, Saturn, Uranus, and Neptune, will see an increasingly dimming sun. But this is not the end, and here's now where I need my last few minutes here. So all this happens on the next part of the cosmic calendar the following year, sort of out to July. But there's a longer-term process that will do in the rest of the solar system, and if we find some way to move the Earth, even do in the Earth. So this is the problem. Jupiter, Saturn, Uranus, and Neptune, and maybe Mars, are now orbiting a star with only half of its present mass. So they're twice as far away as they were before. And that, it turns out, makes it much easier for Jupiter and Saturn to enter directly into this resonance that I talked about, this great inequality. Once they enter into that resonance, any passing stars, as this white dwarf that was the sun moves through the galaxy, any passing stars will easily perturb Jupiter and Saturn into very eccentric elliptical orbits. And the result of that is that the planets will all be ejected. So this is a simulation, a very recent one. This is the ellipticity of the orbit. So 0 is a circle and 1 is a parabola. And this is time. And what you see, this is time actually after the sun has lost half its mass. Over a period between 10 and 100 billion years, Jupiter, Saturn, entered into this 5-to-2 resonance, will eject themselves. There'll be one planet left. It depends on the simulation. In this case, it's Jupiter. But eventually, because it's in such a non-circular orbit, even it will be ejected by the effect of passing stars as the solar system moves through the galaxy. So once the sun becomes a white dwarf, half the mass that it is today, the entire solar system will be emptied. Probably Mars will go as well. If we manage to save the Earth, it probably will be ejected as well, although they're not included in the simulation. So that's the end of the solar system. There's a white dwarf and nothing else. Now, can I have 2 or 3 more minutes? Because no one ever asked me any questions. So, all right, so I want to now end on a historical note instead of a hysterical note. And I hope no one's been disturbed by all this, because it's 100 billion years. So the problem of the stability of the solar system actually goes back to Kepler and Tycho Brahe, because there were observations that were made by the Babylonians that back in the BC era that were transmitted by Ptolemy, that when Kepler analyzed them, and remember Kepler took this complex system of epicycles and circular orbits and said elliptical orbits fit the planets much better. The 2 planets that the elliptical orbits didn't fit were Jupiter and Saturn. It turns out that by fitting data from 2,000 years, you can show that Jupiter is moving in and Saturn is moving out, as Jacques Lescar describes in a paper. If you just assume it's always been that way, you would say that Jupiter and Saturn were in the same orbit 6 million years ago. But in fact, Laplace showed that these were not long-term secular motions, they were actually oscillations. Both Jupiter and Saturn orbits were oscillating closer and farther away from this 5-to-2 resonance on a 900-year timescale. And Newton actually began to talk about the fact that planets could attract each other gravitationally and cause these perturbations. So that became known then as the great inequality. Laplace showed that there were these oscillations closer to and farther away from the resonance, and that it was the strong gravity of the sun that prevents the 2 planets from getting into that resonance. And so they oscillate around it with a period of about 900 years. What these dynamical simulations of the far future seem to show is that that great inequality, once the sun has lost half its mass, is responsible for the final destabilization of the solar system. And so it's interesting that the very earliest observations that were used by Kepler to understand our Copernican nature of the solar system, that the planets orbit around the sun, that the effect of Jupiter and Saturn on each other, this great inequality that was recognized nearly at the beginning of the Copernican era, is what ultimately will do in the solar system. It will empty the entire solar system. So Jesus in the Gospel of Matthew pointed out that heaven and earth will pass away. I've tried to give you a scientific story for how the earth might pass away. And after lunch, my colleague, Father Jonti, will presumably explain how the heavens will pass away. So thank you.